Welcome! The purpose of this video is to go over the SL Paper 2 final exam from 2021 and go through some common pitfalls and common misconceptions. You have access to the presentation that I'm sharing to the right of your screen. In that presentation, I'm going to go through where we saw each problem type in class. You also have access to the mark scheme. So I'm not going to talk through every single answer because you can look that up in the mark scheme. I'm just going to talk about common issues that I saw. All right, so question one. The first thing to notice in question one is that we're dealing with all gases. So we need to use those gas laws that we learned. The first question is asking about limiting reagent. Limiting reagent asks you to find the theoretical yield if carbon monoxide is limiting or if hydrogen is limiting. That means you need to relate your math to the product formed. Some people tried to just tell me moles of carbon monoxide added. That's not very helpful. You need to find how much product would you make. Okay, so for example, with carbon monoxide, I'd set up my math something like this. My ratio to compare my reactant with my product is 2 to 1. I'm using coefficients. And what unit am I going to use? Well, I actually don't need to go to moles because of what we learned on day 11, slide 17. You can use volume ratios. Some issues I saw here, some people tried to write moles, but you hadn't actually converted to moles, so you lost a mark for that. You are comparing volumes directly using coefficients if you have a gas. 2 centimeters of carbon monoxide and 3 centimeters cubed of hydrogen gas yield 1 centimeter cubed of ethane 1,2-diol. Because with gases, the volume always has the same number of moles, regardless of the gas type. All right, so I'm comparing carbon monoxide with my product. So you do this for both reactants, for carbon monoxide and hydrogen gas. You find that carbon monoxide is limiting. You did need the correct work there to get full points. Then, in order to find excess, you need to find, we know that hydrogen is going to be the one in excess because carbon monoxide was limiting. So the amount of hydrogen added, so that's the 1,000 cubic centimeters, and you subtract from the amount of hydrogen that reacted. So here you need to do dimensional analysis to figure out if all 500 cubic centimeters of carbon monoxide react, which they will because CO is limiting, how much H2 will be required. You subtract those amounts, and then you get the excess. All right, in A, you would have calculated the theoretical yield. It would be the yield associated with carbon monoxide because that one was limiting. You then needed to take that amount that you found in A and convert it to moles. So your unit for theoretical yield would have been centimeters cubed from A. And then you need to use this conversion factor that we learned about in, this says homework 8, but it was actually an in-class thing, even though we called it a homework. So that conversion factor is 22.7 decimeters cubed of any gas per mole. So again, your theoretical yield would be in centimeters cubed, so you convert that to decimeters cubed. Then you can use this conversion factor to get into moles. All right, B. B is asking about boiling point. I'm still seeing some people trying to kind of confusing IMF and covalent bonding. And you really, 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 really need to be careful here. So let's draw out what happens when something boils. Here's my ethane 2-diol. And of course, I'm going to have a bunch of molecules. I just have a big sample of it. Okay. And then over here, separately, these are not together. I'm going to draw my ethene. I'm just doing skeletal formulas here. We know that there's carbons and hydrogens wherever I'm not explicitly showing an atom. So when something boils, what happens? Well, the IMF is broken, the interactions between molecules. We're not breaking covalent bonds. That would be if we broke this carbon-carbon bond, for example. That's a chemical reaction. All we're doing when we melt or boil is breaking intermolecular forces. In this case, the intermolecular forces are hydrogen bonds. We know that bonds is kind of a weird word for hydrogen bonds because they're really just intermolecular forces. And in here, the only intermolecular forces we're breaking are London dispersion. So hydrogen bonds are stronger, and so that's why there's a higher boiling point. Be super, super clear when you answer these types of questions that you understand that we are not breaking covalent bonds. We're not breaking this bond or the bond between hydrogen and oxygen. We are breaking all we're breaking is the intermolecular forces, but the molecules themselves stay intact. We're just breaking that thing that connects the molecules to melt or to boil. We practiced that a bunch of times on the slides here. I'll show you one example. All right, 1C. They give you an alcohol being oxidized to carboxylic acid. We learned two oxidizing agents, and remember these were true for any oxidation where there's a primary or a secondary alcohol. Not tertiary, because tertiary alcohols tend not to get oxidized, but in this case we have two primary alcohols. So either of these were acceptable, potassium dichromate or potassium manganate. You could write the whole name or give the formula, but some people here just tried to say oxidizing agent. Yeah, sorry. That's not specific enough. You have to tell me what the oxidizing agent is, like we saw in the slides here. In D, primary, secondary, tertiary with a reason. Most people were able to say secondary, but some people's reasoning was a little unclear. The alcohol itself is connected to only one carbon. Some people were trying to tell me the alcohol was connected to two carbons. But take a look. The alcohol is only connected to one carbon, right? But the carbon that the OH is attached to, that's a single carbon, is connected to two carbons, these two. And that's what makes it secondary. Here's where we practice that in class. You see to the right of your screen. All right, and then finally E, they give you a molecular mass. You just need to convert grams to moles using molar mass. We did that throughout stoichiometry. So here's where we saw molar mass. You then needed to convert to, nope, you just needed to get to moles. All right, so that's question 1. Question 2. A, deduce the equation for the decomposition of this reactant. Well, decomposition, we learned decomposition is when you start with one thing and it breaks down into several things. We saw a video on that at the beginning of the organic chemistry unit. NH2, 3, NO3. All you had to do here was read. Decomposes to form nitrogen gas. We know from these slides that nitrogen is diatomic, so N2 gas, plus water vapor, so H2O gas, plus solid carbon. Carbon is not diatomic, so it's just carbon. And then you just had to balance. And so I think the balancing, if I'm not mistaken, was 2 and 3. Careful with state symbols and remembering to balance. B, again, moles to grams of guanidine nitrate. And then, so moles to grams, this is using molar mass. And then, oops, I switched those, sorry. You actually start with grams, you have grams, so grams to moles using molar mass. And this, of course, is moles of product, moles of reactant, sorry, moles of reactant. And then you need to get into moles of gas in the product, a little tricky. You have two gases. So there's 5 moles of gases for every 1 mole of reactant, 5 moles of gases using coefficients. So this was a little trickier to recognize that there were two products that were gases. C, this was just a PV equals nRT problem. The only issues I saw here were forgetting about the units. Just like you see on the slide, units matter. So you have to convert this to Kelvin, convert this to meters cubed, and then convert your final answer into kPa instead of just PA. 2D, this one people struggled with a little bit. So we talked about that sometimes gases don't behave like ideal gases. So some people were trying to tell me that the gases would become liquid. No, we're still talking about when it's a gas, but we're trying to figure out, is it behaving like an ideal gas or a real gas? So we saw that at lower temperatures, gases tend to have some IMF, right? One of the conditions to be an ideal gas is no IMF. And so if you cool a gas, it's going to start having some IMF. Okay, well, between water and nitrogen, who would have more intermolecular forces? Obviously water, because water has hydrogen bonding. And so just applying what we saw right at the end of the unit there, day 12 in stoichiometry. All right, moving right along. Question 3. One issue I saw here was not remembering atomic notation. This is mass number, friends, not number of electrons. Number of electrons, needed to look up chlorine in the periodic table, find the atomic number, which I believe is 17. Other than that, you all got electron configuration. We practiced that a bunch. Here is one example. Okay, B, physical property. You actually saw this question on topic 2, key assessment. Some of you are still trying to say atomic mass. That's not a physical property of the substance. The atomic mass or the mass number differs between these. So a sample of carbon-35 would have a different melting point, boiling point, density, etc. than a sample of, and I think I just said carbon, excuse me, chlorine-35 would have a different melting, boiling point, density than chlorine-37. So these are physical properties. Chemical properties, the IB is very specific with this question. A lot of you said because they have the same number of electrons. That's true. The IB wants you to be really particular that it's not just total electrons, but valence electrons that really matter. They have the same electron configuration because it's those valence electrons that are doing the chemistry. You could also say here the number of protons equals the number of electrons. This is one of those times you just really have to pay attention to the mark scheme. They're very, very particular with what they accept. Okay, see, people answered pretty well. I was lenient because the boxes that I gave you on the test accidentally said 2s and 2p, and then I asked you for valence. So some of you realized that and just changed this to 3, which is great. Some of you showed me 2s and 2p, which would of course be full for chlorine. So I was pretty lenient there as long as what you wrote made sense. 3C, again, there were 2 C's, which doesn't really matter when you're taking the test. But anyway, chlorine atom or chlorine ion has a larger radius ion because more electrons, so there's more repulsion. And we saw that in periodicity. You should have had that written down in your periodic trends guided notes. Why does a chlorine atom have a smaller atomic radius than the phosphorus atom? Well, look at where they are in the periodic table. They're in the same period, but chlorine is further to the right. So chlorine has same number of energy levels. When you add more electrons, you're not creating more repulsion, but more protons. And so it pulls the electrons in tighter. Okay, mass spec. Outline the reasons for 2 peaks. Of course, peaks represent isotopes. So chlorine has a mass of 35 isotope or mass of 37 isotope. Um, this was a little tricky. Chlorine is diatomic. So we saw those peaks at 74. Well, that comes from the way that chlorine would actually exist in nature. So you'll notice, I think I just said 34, sorry, 74. That comes from having two chlorine 37s forming a peak. So the key was remembering that chlorine is diatomic, and I actually gave you this little hint. This was not from the IB, this was from me to prompt you thinking about diatomic. All right, moving on, question 4. A lot of people were trying to tell me about how an ionic bond forms. We spent a lot of time in class talking about electrostatic attraction and bonding, both for covalent and ionic. So another example, the IB is really specific. I gave you IB language here in the slides. This was from topic 4 slides, part 2. And you can see ionic bonding, electrostatic attraction between positive and negative ions. You needed to have positive and negative ions, and you needed the words electrostatic attraction here. Again, IB is very particular with definitions. Whenever I give you slides and I'm giving you specific IB language, that's the language that you need to know. People did pretty well with this. Here's an example to the right where we practice this, just remembering where the valence electrons are. And of course, we remove electrons in the highest energy level to form a positive ion. So if we take a look there at the periodic table, calcium is right here. And so 1s, 2s, 3s, 4s2 would be the highest for highest energy level for neutral calcium. So you're removing 4s2 electrons and ending with 3s6, just like argon, for the ion. Hopefully that was clear. Here, the issue that I saw was some people wanted to say that color comes from when light is absorbed. The color is actually released when an electron relaxes back to the ground state. So we talked about that here. I'm showing you some examples. We saw a gizmo where you saw the electron get excited, jump energy levels, and then it's not until the electron relaxes to a lower energy level that it releases a photon. So you had to be really, really clear that the source of the color is from the electron relaxing. Then why are they different colors? We talked about that here. On the slides, you see we have different colors because sodium and what was the other one? Calcium have different electron configurations and specifically different energy levels. And so if you're moving from different energy levels, you see here in the hydrogen emission spectrum, if you're moving from different energy levels, you'll release different colors. All right, question 5, moving right along. So you'd seen this exact problem before, define the term electronegativity. So again, whenever you're defining terms, you need to pay attention to my mark scheme. That's when you should really be using those homework mark schemes. You need to use IB language. They're very, very particular. So you need to mention atom being attracted to bonding electrons. B was very similar to the chlorine phosphorus thing, just kind of a bigger general trend. And whoops, sorry, I got one ahead of myself with the slides here. But again, Zeph is your friend here. So increasing nuclear charge was worth 1 point. Same energy levels was worth the second point. And then in C now corresponds to what you see on your screen here. This was just an equation we learned with all alkali metals. Lithium is an alkali metal. So lithium and water form metal hydroxides and hydrogen gas. That's just an equation you have to know that we saw in class. D, People struggled a little bit with D, and sorry, my numbers are off here on the slides, but this should be D. Um, they wanted a compound, not a reaction. So you're looking at where these are in the periodic table and how many each atom needs to get to an octet. So lithium is in group 1, oxygen is in group 16, so needs 2 electrons. Group 1 is going to donate its 1 valence electron in order to get to 8. So you'll need 2 lithiums for every 1 oxygen. Very similar with beryllium. Beryllium's group 2, nitrogen is group 5. So beryllium is going to try to lose its 2 electrons. Nitrogen needs to gain. Actually, let me do that better. Beryllium is going to lose 2 electrons, tend to lose 2, so it'll have what we call an oxidation state of +2. Nitrogen is going to need to gain 3 negative things, so it'll get to an oxidation state of -3. So in order to form a neutral molecule, we need 3 berylliums and 2 nitrogens. E, where did we see E? Well, it asks you for Lewis structure, shape, bond angle, and why it's polar. So Lewis structure, here's where we saw how to draw a Lewis structure. So most people did pretty well with this. The one thing that I saw was not remembering the lone pairs on fluorine. So Lewis structure, you do need to show all lone pairs. Shape, here's a good example. We actually saw sulfite. This has the same shape, right? 4 electron domains. So shape was general. I accepted either molecular geometry or electron geometry. So you could have either said tetrahedral or trigonal pyramidal, either electron geometry or molecular geometry there, or trigonal pyramidal. The bond angle, this, you did need to be specific that it's less than 109.5 degrees because we do have lone pairs. We know that pushes these angles to be a little bit smaller, so you might have said something like 107 there to get full points. All right. Question. Oh, and then if it was polar, you need to look up the electronegativities. And some people also mentioned it's not symmetrical. That was great because they are looking at the whole molecule. All right, question 6. So here in A and B, this was a free radical substitution. I have ethane and a halogen. I have a alkane and a halogen. That's free radical substitution. So big picture reaction, you see here from slide 17, big picture reaction in A, full mechanism in B. And then this thing that we form in B reacts with sodium hydroxide. Well, we learned that OH minus is a nucleophile, and it's really the only nucleophile that we've seen. So if I have OH minus hanging out, I probably have a nucleophile, meaning I'm going to have nucleophilic substitution. So the type of reaction is nucleophilic substitution, and then we're looking at that sodium hydroxide specifically, and I'm asking you how you'd prepare it. I told you in the stoichiometry unit, guaranteed this would be on the assessment, how to prepare a solution. It's just critical to understanding stoichiometry and solutions is knowing how to actually make them in the lab, and it's part of the core curriculum. So I've given you this exact problem before in the homework. If you added 2 of the details that you see on the slide here, you got those 2 points. All right, ending with question 7. So first, naming. The one thing I saw with naming this molecule was people were trying to give it numbers. All numbers here are actually redundant. So this methyl group, this is the only carbon you could put this methyl group on and still have it be a methyl group. Because if you put this methyl group on carbon 1, well, then the methyl group wouldn't be a methyl group, it would just make a butene chain. Same thing if you put this methyl group on carbon 3, right? It would be, oops, sorry. It'd be the same thing. It would just add on to the chain. So the only situation in which this could be methyl is if it's right here. And so that means I don't need to put the number. And then propene, well, again, there's no way I could number this in which there's different molecules. Like butene, all right, these are two different molecules, and I see that they can have different numbering, but there's only one set of numbering that's possible for propene. So I'm actually not, so actually any numbers are redundant. I give credit if your numbers made sense. I will be honest though, I'm not sure if the IB would. So that's something to pay attention to in the future. Is your numbering necessary? In this case, it is just methylpropene because any numbers are redundant. This is, if I write methylpropene, this is the only molecule that I could make. Whereas if I wrote butene, well, I could make but1-ene or but2-ene, and these are two different molecules. But with methylpropene, this is the only molecule that I could make and have it fit methylpropene. So butene, we do need numbers. This is but1-ene and but2-ene. With methylpropene, we do not, and actually we should not put numbers. Polymerization, people did pretty well with this. You need to be able to go from a monomer to a polymer. So if you didn't get that one, take a look at the mark scheme, figure out why not. You need to be able to go back and forth between monomers and polymers. And we've practiced that before. So if you're not feeling sure on that one, use the mark scheme. And if you're really, really not feeling sure, you need to ask me specifically because that's a skill that you should have at this point. All right, complete combustion. We learned that complete combustion is plus oxygen yields CO2 and H2O, so you needed to get the molecular formula here. And then write out the molecular formula plus oxygen yields CO2 plus H2O. You put the molecular formula here, and then balance. Some people were trying to write CXHY like you see on the slide. You needed to actually use compound A. Compound A and B, those are examples of isomers because they had the same molecular formula. And then final question. I was surprised that this one didn't go as well as, maybe just because it was at the end, as well as I expected. You saw this. The only chemical test that we had really was the bromine test. One student was really creative and said maybe they have different melting points. So you could try melting them and see which melts sooner. That would be a physical test, though. Really, the only chemical test we saw in that unit was the bromine test. So you have here on the slides the bromine test and exactly what they accept in terms of discussing the results. When they ask you to include an observation for each, you do actually need to mention each molecule. Some people just mentioned A or B, so be careful. And remember, when you're making the observations, they do not give credit for the word clear. You must use the word colorless. All right, I hope that helped. Any questions, let me know. I'm happy to answer them. Thanks for watching.